So it's been a bit of a nail-biting couple of weeks for Mars fans out there, huh? Yeah, exactly. So first we have that unfortunate eerie silence from Beagle 2, which is the Mars Express lander that was due to land on the surface of the planet on December 25th, and we haven't heard anything from. Uh-oh. And of course, tomorrow at 11:50 or 11:35, I should say, Eastern Standard Time, the Mars Exploration Rover Spirit is due to touch down on the red planet's uncertain surface. The perils of landing safely, even after that toasty entry into Mars's atmosphere, are numerous, but if successful, Spirit will be NASA's roving geologist, sampling rocks and testing the environment through a variety of cameras and spectrometers to paint a picture of our red neighbor that we've never seen before. So it's pretty exciting. Tonight's speaker, Dr. Maria T. Zuber, is part of the mission team that will act as consultant to this rover once landed. We're very, very fortunate to have Dr. Zuber here tonight. She's actually flying off to California's Jet Propulsion Laboratory, which is mission control, as many of you know, tomorrow morning. So we better let her go after the lecture tonight so she can get a good night's sleep. Dr. Zuber is one of the most respected geophysicists, pretty much solar system wide. She's the, sorry, I had to do it. She's the head of the Department of Earth, Atmospheric, and Planetary Sciences at MIT. She served as the E.A. Griswold Professor of Geophysicist of that department since 1998 and has been a professor at MIT since 1995. She's also been senior research scientist at NASA's Goddard Space Flight Center since 1994 and has been involved with Goddard since her grad school days back till 1985. Dr. Zuber was awarded her PhD from Brown University in 1986 in geophysics. Dr. Zuber's list of awards and honors is long, and her NASA planetary mission participation is also huge. I'll just mention a few. She is the deputy principal investigator of the altimeter on Mars Global Surveyor, which is currently surveying Mars. She's the co-investigator of NASA's Dawn mission to Vesta and Ceres. She's the team leader of Radio Science Gravity Investigation, the 2005 NASA Mars Reconnaissance Orbiter mission. She's also co-investigator and lead of the geophysics investigation NASA Messenger mission to Mercury. And this is just a handful of the things that she's doing. But tonight, Dr. Zuber is going to be helping us ponder a little bit about our red neighbor and a little bit about what Spirit might find when it lands tomorrow, hopefully. Of course it will. Mountain ranges, water, maybe even life. So without further introduction, please help me welcome Dr. Maria Zuber.
Okay, thank you very much. It's a great time to be involved in Mars or to be interested in Mars. And what I'd like to do tonight is to share with you a little bit of excitement that I have every day of my life, okay, because I don't have to work for a living. I get to study the planets for a living, okay. And given that it's the holiday season, I thought we'd start with a nice picture up here. For all the kids in the audience, this is the North Pole of Mars, okay. This is a topographic image that we first published in December of 1998, and it's actually relatively low resolution compared to some of the things that we observed after that, but it's always been one of my favorites. And this actually wasn't taken from a camera. This was actually taken by shooting laser pulses off the surface of Mars and getting the reflections and assembling an image out of that. And so what I'm going to try to do tonight is this talk is going to be in three parts. The first part of the talk is going to talk about Mars today, what Mars is like now and what these rovers are going to see when they go there. The second part of the talk will be Mars a long time ago, why Mars is different, what it was like a long time ago, and a little bit about why it changed, okay, because Mars has undergone significant climate change. And then the third part of the talk is going to be about landing on Mars. And I'll walk you through a little video that's going to show what's going to happen if all goes well tomorrow. Okay, so let's get started here. This is a comparison of the Earth and Mars to scale. Okay, Mars is about half the size of the Earth. Okay, it's actually about the same size as the Earth's core, to within a couple of 100 kilometers. It has about the same surface area as the Earth's continents. So the land surface area on Mars is about the same as the land surface area on the Earth. There are some things about Mars that are very, very similar to Earth, and you'll see some pictures where you could say, this could be Earth, this could be a place I know. And there are some things about Mars that are very different. Gravity is about a little more than a third of what it is on the Earth, and this is going to be significant later because things bounce higher on Mars. Mars is 1.5 times as far from the Sun as the Earth is, so it doesn't get as much solar radiation from the Sun, but it still can get warm. The Mars is tilted on its axis. Okay, the tilt of the spin axis is actually 25 degrees, and Earth's is 23.5 degrees, so it's very similar, and that's entirely coincidental, okay, because it actually varies on both planets. And we all know that because the Earth's spin axis tilt, the Earth goes through seasons, and Mars's spin axis tilt, so Mars goes through seasons too. And one Mars year is 687 Earth days. Okay, so it's about 2 Earth years. So when we send an orbiter to Mars, we always send it there for 2 Earth years, which is so we can observe Mars over all its seasons. Okay. And the length of a day, this is also coincidental. On Earth it's 24 hours, and on Mars it's 24 hours and 37 minutes. And 24 hours and 37 minutes sounds a lot like 24 hours, unless you happen to be living on Mars time, which is what happens when you put a lander on the ground. And after about 2 weeks, you're in constant jet lag, okay, because you've got to add 37 minutes to your day, and your circadian rhythms don't work that way. Okay, so that's a little bit about Mars. A little bit about the environment at the surface of Mars. Mars, as many of you know, has predominantly a carbon dioxide atmosphere. The average surface pressure at Mars is about 1/200th of what it is on the Earth, so it's equivalent to an altitude of about 100,000 feet on the Earth, which is the altitude at which spy planes fly. Okay, so we talk about the Martian atmosphere, but in practical terms, it's practically a vacuum. Okay, the surface pressure varies by as much as 30% over a year. The carbon dioxide atmosphere snows out, okay? And one of the things that I've done in my research is measure how deep the snow gets on Mars, how deep the dry ice snow gets on Mars. And just to give you a comparison, on the Earth, the biggest pressure drop that we see is in a tornado, and we've never actually measured that successfully, but there are some interesting stories about trying to do that. In hurricanes, as the eye of a hurricane, you can get a 10% pressure drop. Okay, so the pressure variations on Mars are much more extreme than they are on Earth, because this happens all over the planet. Okay, water vapor. There isn't much water in the Martian atmosphere. It's 0.03%, and what that actually corresponds to, if you took all the water in a column of atmosphere and you scrunched it down, okay, into a layer, the layer would be 10 microns thick, where a micron is a millionth of a meter. Okay, so water isn't abundant in the atmosphere, but it's actually quite important, because we do see things like water ice clouds. The average surface temperature is about minus 53 degrees C or minus 60 Fahrenheit, which is 20 or 30 degrees colder than it is on an average day at the top of Mount Everest. Okay, so Mars is a freezing place. Okay, however, in the summer, if you're down at low latitudes, like where these landers are going to land, the temperature right at the ground, at the surface, can get to be in excess of 70 degrees Fahrenheit. Okay. However, that's at your feet. Okay, because the atmosphere is so thin, it doesn't have the capacity to hold heat. So your feet could be warm, but your head would freeze. Okay, because the temperature would drop off 40 or 50 degrees by the time you went from your feet up to your head. Okay, so it's quite an interesting place. Now, one thing that matters a lot to us who try to land things on Mars is dust. Okay, and dust may not sound very interesting to you, but it's actually fascinating. Mars is a very dusty place, and I'm going to be showing you some pictures of dust and why it's important for trying to land on Mars. And finally, liquid water is not technically stable at the surface of Mars today. The pressure temperature conditions are such that it's cold enough and the atmospheric pressure is low enough that if you poured water out of a pitcher there, it would just boil into the atmosphere. But I'm going to show you evidence that small amounts of liquid water can actually be metastable and can, kind of melt underneath the surface and drip out even today. Okay, and so let's go on. Okay, first thing we're going to talk about is dust. Okay. Mars is a very, very dusty place. The dust is about 1 micron in size, so of a millionth of a meter in size. So the dust gets lofted up into the atmosphere, and the dust storm season occurs every southern hemisphere summer on Mars, okay? And we're going to have a landing on Mars tomorrow, and guess what season it is? Southern hemisphere summer. Okay, celestial mechanics dictates that this is when we land on Mars, and it seems like we're always landing on Mars in dust storm season. Okay, you get to launch, because of the configuration of Earth and Mars, you get one launch to Mars every 26 months. Okay, and so this is a picture of a dust storm front on Mars. Here's a dust storm blowing off the North Pole, and here are reflections across the terrain. These are reflections from the atmosphere of dust particles in the atmosphere, so it's a little bit like a sandstorm. Okay, and let's see. Here is this is a measure of a parameter called opacity, for those of you who have a scientific bent to you, but it's basically a measure of the dustiness of the atmosphere, and blue corresponds to a clear atmosphere on Mars, and red corresponds to a dusty atmosphere on Mars. And this runs from June 17th, 2001 through the end of August of 2001, and this was the biggest dust storm that we've ever observed. And what happens, these things starts in southern hemisphere summer, so you see the dust storms actually kick up by the winds blowing off the polar cap, okay, because you have temperature differences. The temperature differences drive pressure differences, so you get winds blowing off the south polar cap. They kick up dust storms. If the conditions are right, these things can go global in a week or so. They envelop the planet. The dust is 1 micron in size, so it stays in the atmosphere even though the atmosphere is thin. And then what happens is you get the dust, when it's in the atmosphere, it warms the atmosphere because dust can hold heat a lot better than molecules of carbon dioxide can. So that causes the atmosphere to heat up even more, which makes Mars windier, which kicks up more dust, and so it just goes crazy until you get so much dust in the atmosphere that the sun can't get in anymore, okay? And then it starts to cool out, and then it can take as long as 6 months for the dust to come out of the atmosphere. So we are fortunate that there is not a global dust storm going on right now when we land tomorrow. Okay, this is two pictures from the Mars orbiter camera that is on the Mars Global Surveyor spacecraft now. This one taken before the dust storm, and this is when the dust storm is in full view. So you can see how dusty the planet gets. So you can't even. It's very, very difficult to use an optical camera to get a nice sharp image of Mars because the atmosphere is always dusty. Okay, actually we've had more success getting images with good contrast on Mars by using either spectral or laser techniques to do the imaging. Okay, all right. This isn't the image that keeps me awake at night. Okay, the mechanism for lofting dust in the atmosphere of Mars we now understand. Okay, it's by something called dust devils, and dust devils are essentially a dry tornado. Okay, and this is a picture of a dust devil that was taken by the Pathfinder rover. Okay, in 1997. This is a picture of these are laser returns where we actually hit a dust devil, so we can actually see how high the dust gets lofted up into the atmosphere, and we can actually say something about the dust density. And what you see on the right-hand side here, and this is what gives me chills. These are dust devil tracks. Okay, so in the atmosphere of Mars, in the middle of the afternoon, when the sun heating is the greatest, you see these dust devils all over the place at low latitudes, and this is where we're landing tomorrow. Okay, it used to be that we always landed spacecraft on Mars at night. okay? And we did it because the atmosphere is calm, okay? However, in 1998, you may recall that we lost a lander, okay? And that lander was going in, and it turned out I was on the failure board for that lander. We actually figured out why that lander crashed. I'm going to talk a little bit about that later. However, because of the fact that it was behind the planet at night when it was going in for us at Earth, we didn't get any telemetry when it was going in. So there was a chance that we might not have ever figured out why it failed. So as a consequence of that review, there's now a rule that you have to be in communication with a lander as it's going in, so that if it fails, you know at what point it fails, so at least you learn something from the experience. But that also means you have to land in the middle of the day when the sun is the hottest and when it's the windiest and when you have the greatest chance of being bothered by winds. Okay, so that is dust. Now I'm going to talk about water on present-day Mars, but water in the frozen form, first of all. Okay, this is these are profiles of topography across the North Polar Cap over here and the South Polar Cap over here. The polar caps have about 1 meter or 2 of carbon dioxide snow that vaporizes over the summer, and both polar caps are made of predominantly water ice, H2O ice, okay? And because of the fact that we can measure this very precisely, we now know the volume of water ice that is right at the surface of Mars, and if you add both of those up, you find out that the amount of water ice on the surface of Mars is about 85% of what we have in the Greenland ice cap, okay? So that's kind of a lot of water, but it turns out that there's even more water ice beneath the surface, okay? The previous discovery was made by Mars Global Surveyor. Here's a magnificent discovery that was made by Mars Odyssey, which is also the other orbiter, which is in orbit around Mars right now. And Mars Odyssey has gamma ray and neutron spectrometers on it that actually detect neutron fluxes that come in from cosmic rays hitting the ground and interacting with atoms. And basically everything that is blue on this map corresponds to a high water ice content within the top meter of the surface. And when you get up to high latitudes in the northern hemisphere, there are some areas where the water ice content is greater than 90% by volume water ice. Okay, so it's basically dirty ice in the top. So there's just vast amounts of frozen water near the surface of Mars. And this is just an absolutely fabulous discovery, because we are going to send people to Mars someday, and we used to think that we were going to have to drill to get it, and now you can take a shovel because there's so much of it's there and it's accessible. And so this is just a fabulously important discovery for future Mars exploration. Now I'd like to switch over and talk about, instead of water in the frozen state, let me talk about water in the liquid state. Now I told you that at Mars's pressure temperature conditions today that water boils away right into the atmosphere. However, there are features that are on the surface which look like a little bit of water somehow melted from the frozen state and dribbled out and started flowing downhill. And there is even better evidence for this. Here's another sort of feature. This is something called slope streaks. You see these things. They only occur on sloped surfaces. They only occur at certain latitudes. This is a map of Mars, and actually this is some work that was done by one of my former graduate students who looked at all of these images. Okay, and if you look at he went up over 65,000 images, and if you do that and if you discover what he discovered, you walk right into a professorship at Caltech when you finish, okay? And the red shows no slope streaks, and the black images show slope streaks in them. And you can see they only occur at equatorial latitudes. They only occur on sloped surfaces, and you only see them in places where the temperature gets above the melting temperature in the summer, okay? And so these are evidence that liquid water is actually flowing on the surface in the present day. And how do I know in the present day, in this year? Okay, because you see new ones form. Okay, so you take an image at one time. This is taken in August of 1999, and you see a slope streak here. And then you come back in 2001, one Mars year later, okay, and you see that one, and then you see a new one, okay. So small amounts of frozen water are melting and dribbling out. And when we talk about how much water is this is not lakes of water. This is swimming pools of water. So it's tiny amounts of water, but water can be in the liquid state for a small amount of time. This is another discovery. Basically, everything I'm telling you here today has been discovered since 1999. Okay, now we're going to go back in time. Okay, unfortunately, we are not sending the rovers to the areas where these slope streaks are for two reasons. Okay, the first is that they were discovered so recently that there wasn't the time to design an experiment to go see them, because you design these experiments several years before you send the missions. And the second thing is these areas, although they're very interesting in a geological sense, you can't get there. Okay, they're all on hills. Okay, you can't send a rover up a cliff. Okay, we don't have rovers that can go up cliffs. So we are in the process of trying to figure out how to make rovers that can climb. Okay, however, we can't do that yet, and so the purpose of the current rover mission is to actually look for areas where people believe there used to be liquid water on the surface of Mars, and not swimming pools worth of water, but vast amounts of water. Okay, so we're going to go back in time now, and I'm going to show you evidence that there was in the past what appears to have been large ocean-like amounts of water that existed on the surface of Mars. But first, we need to adjust our thinking here and get a little bit of a feel for what the time scales are that are involved. Okay, so here's the time scales of the Earth, and this line here corresponds to today. Okay, and this back here is when Mars formed and Earth formed 4.5 billion years ago. Okay, now here I've blown this beige area up here for the Earth because modern-day humans appeared about 2 million years ago. The dinosaurs went extinct at this white line here 65 million years ago. All of the ocean basins on the Earth are younger than this. And then when we get back here, this is virtually none of the Earth's surface is this old. Just small amounts of the Earth's surface are that old. Okay, virtually everything on the Earth is about 200 million years old or younger. Okay, but then when we go to Mars, most of the surface of Mars is from 3.8 billion years old or older. Okay, and this is a stratigraphic period on Mars that we call the Noachian. And this is named after a type area on Mars called Noachus that was named after Noah for the flood. Okay, and so Noachus is an area where there were significant amounts of liquid water on the surface. And so the area that we're going to be looking at is not today. Today's Mars is where you get a little water dribbling out. Okay, but past Mars, Noachian Mars, we think there were vast amounts of water. So when you look at that, you can look for evidence of water on the surface. But we also have in our collection of meteorites a rock that is 4 billion years old that came from Mars. Okay, and basically, I always get asked, how do you know this rock came from Mars? And actually, there are a number of reasons that I could give you, but the most understandable reason that I can give you is that these rocks contain vesicles that have gas compositions in them. And gases that are of particular interest are gases called noble gases, which if you've had chemistry and you know the periodic table, there's those elements down at the end because they don't combine with anything because all their electrons are filled in their shells. And because they don't combine anything, what their abundances are very indicative of where they came from. And the abundance of gases in these meteorites are unlike anything at all anywhere on Earth, but they are an exact match for the atmosphere of Mars that was measured by the landers that went in. Okay, so it's a done deal. This rock came from Mars, and it formed 4 billion years ago. This rock has evidence of what has been proposed to be nanofossils. This is very controversial evidence. Okay, but this is the period of time that we're going back to look at. Okay, and so let's look at what Mars was like in the period of time when these features formed. Okay. it looks like this. Okay, you see teardrop-shaped features that indicate something flowing on the surface and leaving a shadow right there. You see valley networks and channels. You see evidence for vast, catastrophic outflows of waters. These are just maps here, so you can look at the location on the surface of all these nice images that I'm showing you. Here is an evidence of catastrophic flow. This is the Pathfinder landing site, and all these big rocks were things that were deposited by being carried by vast flooded amounts of water. Okay, so in trying to understand how all this occurred 4 billion years ago, it makes a lot of sense to take a look at the whole planet and see what you've got. Okay, and what this is a slice of Mars down the prime meridian, 0 longitude on Mars, and this is a slice of what the topography looks like, starting at the South Pole and going up to the North Pole. And what you see here is that if you started at the South Pole and you started walking north, you would be walking downhill the whole way. Okay, this is just a remarkable feature about Mars. Everything on Mars flows northward. Okay, and the southern polar region is 6 kilometers higher than the northern polar region. So anything that flows on Mars is going to flow to the north. Okay, and this is quite remarkable. This is a crater. Let's see if we can just go backwards here. Whoops, I'm going in the wrong direction. Yep. Okay. The crater that I'm going to show you next is this crater right here. Okay. It's an impact basin called Argyre. Okay. And there it is. Okay. And what we've done over here is Mars has so much topography you run out of colors because it's got a lot more topographic range than Earth does. So we stretch out the color scale and we saturate the top and the bottom. And what you can see here is that there is a channel that flows out of this crater and goes all the way up, and the Pathfinder landing site is right here. So this 1,200 kilometer wide impact basin was once a lake or a sea, and it was filled with water, and it overflowed and it flowed north. Okay, and if you start taking the topography of Mars and filling it up with water, okay, everything green here flowed into Argyre. Everything orange flowed into this basin Hellas, and it stayed there. Okay, now Argyre overflowed, so everything that was here flowed north. And all this stuff in here flowed into the northern plains. And depending on how much you filled Mars up, as much as 90% of the surface could have drained into the northern hemisphere. And this is the area where we think that Mars once had an ocean. Okay, now let me show you some additional evidence for and against an ocean on Mars. Okay, it's not a done deal. It's a strong case, but it's not definitive. Okay, this is a model. This is a plot here of slopes on Mars, and you can see that there are some areas that are very flat. And this white line here is shown in profile right here. So this is a topographic profile that's going across this flat area in Mars. And what it's compared to is flat areas that we have measured on other planets. So this is the flattest area of the Moon, the flattest area of Venus, the Sahara Desert, the abyssal plains in the Atlantic Ocean off the coast of the Falkland Islands, the Great Plains, and the Tibetan Plateau. And this is a little piece of this profile that's taken out of here. And you can't read this, but this is just a few meters in elevation difference over many hundreds of kilometers. And you can actually go for hundreds and hundreds of kilometers on Mars where the change in height is no greater than my height. You can go for hundreds of kilometers where the change in height is no more than 2 meters. And Mars is basically flatter than the Midwest. Okay, it's flatter than the Sahara Desert. The only thing that's comparably as flat as it is the ocean basin, which is a depositional basin. Okay, so this is one of the pieces of evidence that's given for an ocean being on Mars, that it's so flat that it's got to be just sediments falling through water. Okay, however, this is 4 billion years old. We don't have any 4 billion year old wind-blown surfaces on the Earth, so you can't rule out just on the basis of the flatness that it isn't just wind scouring it and making it flat. You need better evidence than that. People have mapped Mars, okay, and this is the largest volcano in the solar system here, Olympus Mons, and this is northwest of Olympus Mons, an area in a box right here, and this is a region that's thought to be an ancient shoreline, okay. However, this is a subjective interpretation. We don't have any 4 billion year old shorelines on the Earth, so that's two people could interpret that differently, okay. Now, one piece of evidence that acts against an ocean comes from chemistry. Now, forget all of this stuff unless you like chemistry, okay? What's important is this map right here. If you have a planet with a carbon dioxide atmosphere and a liquid water ocean, if you mix carbon dioxide and water, you should get calcium carbonate or limestone, okay? On the Earth, the abyssal ocean basins, limestone everywhere, okay? Even though we only have a lot less carbon dioxide than Mars has, okay? On Mars, we only see trace amounts of calcium carbonate, and it is believed that if there was an ocean, you should be seeing a lot more. There's a possibility that it's all covered with dust because Mars is so dusty. So one of the things that the rovers are going to be doing is digging around and moving the dust around to see if they can find carbonate, okay? Because we haven't found it from orbit, okay? One of the big questions is the persistence of water on the Martian surface, okay? We know that water flowed in vast amounts, in some places catastrophically. Some of that evidence that I showed you is really definitive evidence, I think, okay? However, what's important is the length of time that water was actually in the liquid state on the surface, okay? And this is important for biological reasons, okay? Because on the Earth, everywhere that we have liquid water, we have life, okay? And you can't get life forms forming in ice, okay? Life as we know it, forming in ice, unless you have liquid water in the interstices, okay? So if you had a situation on Mars, so the story goes, where the whole planet was frozen, it was cold, and you had some volcanic intrusions that melted subsurface ice and caused an outflow, and then it froze over a year later, okay? That makes the possibility of having enough time for life to develop a lot less than if you had a liquid water ocean that persisted on the surface for millions of years, okay? And so one of the things we look for is what evidence do we see on the surface that water in the liquid state lasted for a long time, okay? Here is one piece of evidence that that was the case. This is a meandering stream bed. If you look down here, you can actually see the evidence of where the stream flowed, okay? You don't form meanders in catastrophic outflows, okay? Meanders form, okay, due to changing sediment loads, and they form over periods of time. The fastest meanders that have formed on the Earth have occurred in New Zealand in alluvial, unconsolidated material in 8,000 to 10,000 years, okay? In bedrock, which is what we have right here, hundreds of thousands to millions of years it can take to carve meanders. And this is carved, this is over a kilometer depth right here, so it's Grand Canyon-like, okay? Here's another, this is a paper that was published in Science last month, okay? So the discoveries are continuing with great frequency. Here's another area, and this is along this same channel where all the water overflowed from Argyre here. And this is north of a crater called Holden. And the next slide here, we're going to focus in on this area right here. And there are two interesting things here. This whole feature right here looks a lot like a river delta. Okay, and the definition of a river, of a delta, okay, is something where sediment gets deposited underwater from a flowing stream. Okay, so this is evidence that seems to be good evidence that sediment was deposited underwater. So water had to be in the liquid state long enough to deposit this material. Okay. Here's another piece of evidence that is in some ways related to the meandering stream that I showed you in a different area before. This is do you know when rivers change their patterns and meanders, they cut off some of their meanders, and they form something called an oxbow lake. Okay, well, here's a meander cutoff. Okay, and so this was once an oxbow lake on Mars. Okay, and this is a brand new discovery. This is a month old. Okay, and it's just an absolutely again a remarkable discovery. It takes a while to form a meander. You don't get a meander cut off from a catastrophic outflow of water, and you certainly don't get an oxbow lake, okay, from a catastrophic outflow. So this is evidence here that water was in the liquid state for some period of time. Okay, now, if we, where did all this water come from, okay, and how did it manage to stay in the liquid state for so long? Okay, well, on Earth, our oceans and our atmospheres came from volcanoes. Okay, if you look at lava that like comes out of Hawaii, your average Hawaiian lava has about 2% water, H2O, and maybe 0.5% or more of carbon dioxide. Okay, this is an area on Mars called Tharsis, and all these features here are volcanoes. And in fact, the whole area here, it takes up 1/4 of the surface area of Mars, and it's a volcanic rise. Okay. And we now know, for reasons that I don't have time to go into, that this is a very old feature, that it formed 4 billion years ago. We used to think that it formed over full Martian history. We now know that it was largely in place by about 3.8 billion years ago. And if you took all of the lava that is associated with building these volcanoes and this rise, and you said it's similar to Hawaii, which it certainly is spectrally, and you said how much of an atmosphere could I have and how much water could we put on the surface? Well, if we want liquid water to be stable on the surface of Mars, you need an atmosphere that's not 6 millibars. You need an atmosphere that's a bar. Okay, a bar, 1 to 2 bars. Okay, if you degassed associated with the volcanism associated with Tharsis, you get 1 to 1.5 bars. Okay, so that's where your thick atmosphere came from. It also can release the equivalent of about 120 meters thick layer of water over the entire surface of Mars. So there's just a vast amount of water that can be released by volcanism. So then the big question is, okay, if this happened 4 billion years ago, where did the water go and where did the atmosphere go? These were two questions that we didn't know the answer to a while ago. We now know the answer to one of them. We know that the water's still there. It just went underground and it's there as frozen water ice. We don't know where the atmosphere went yet. Okay, we don't know how Mars went from a 1 to 1.5 bar atmosphere to 6 millibars of atmosphere. There are lots of good ideas for how you lose atmospheres from planets. If you plug those numbers in for Mars, you can't lose the atmosphere. Okay, so that's one of the things that we are working on. However, it is clear that we had lots of water on the surface. It probably came about by volcanism. And so when we go and when we want to look for evidence of past environments, okay, there were choices of where to put the landers down, and one is being put in an ancient lake bed, and one is being put down in an area with an interesting chemical signature that looks like a hot spring. Okay, so this is how much water we think Mars had. So if you degassed Mars due to the formation of that volcanic province, you would form an ocean in the northern hemisphere that was about 600 meters deep. And if you filled up some of the impact basins in the southern hemisphere, they can be many kilometers deep. So this is what we think the Mars of 4 billion years ago looked like, the Mars that was there when that meteorite with the unusual features formed. Whether that's a fossil, I don't know, okay? And people have been looking at it, and they don't know. But what we think we do know is that this is what Mars looked like, so we're making progress. Okay, so now we're going to talk about landing on Mars, okay? And let me give you a little bit of history here, okay? Robotic exploration of space is a risky business, okay? And there isn't a very, very high success rate going to any planet, but the success rate of sending spacecraft to Mars has always been low, okay? And of course, the smartest people in the world work on this, and these are rocket scientists. And course, we don't blame ourselves for what happens here. So, the lore formed that there was something called the Great Galactic Ghoul out there who had an affinity for spacecraft, and in particular Mars spacecraft. Okay, and you may have read in the paper that a lot of Mars spacecraft has been lost. This is my own accounting here of the success rate of Mars spacecraft. So these are spacecraft that have been sent to Mars. Red indicates that they were unsuccessful. White indicates that they were successful, and I have been very liberal in my criterion for success. If we got anything back, I declared it a success. Okay, all right, okay. And what you see is basically that we're losing to an apparition here. Okay, we're about 40% of Mars spacecraft have succeeded. About 60% have failed. These are the next two that we're going to have results from. But it gets, when you start to look at the landers only, okay, the situation gets a lot less favorable. Okay, only 25% of Mars landers have succeeded. Okay, they have all been U.S. landers, and they have all been landers that have landed at night when the atmosphere is calm. Okay, and so this is just to give you a sense of the challenge that we have ahead of us, okay? And believe me, I have a lot of people that say, why would you want to do this if this is your odds of success? And I say, well, there's a lot more reason to do this than to do something where there's a 100% probability of success, okay? Because that wouldn't be very interesting. We wouldn't be learning very much because everybody else would have done it and we would have known everything already. So I think from just what I've shown you, you can see how much you've learned, that we've learned about Mars just in the last 4 years from this success rate that we have. Okay. Now, let me talk a little bit about the challenges of landing on Mars. Okay. The first one that I want to talk about is the Mars Polar Lander. Okay. This is some terrains in the south pole of Mars. And this is the landing ellipse of where the lander landed, okay? And that lander failed due to a software glitch, okay? It was actually the software executed as written, but there was an error in the designation of the software, of how the software was defined, okay? However, if everything about that lander had been done absolutely perfectly, and if the lander functioned as hoped, okay, it still would have failed, okay? And here's the reason for that. Within the landing ellipse, it turns out that there was a hole, okay? The lander had the ability to land on a slope of up to 8 degrees, okay, which was, at the time we looked at the data, the week before the landing, all the slopes within the landing ellipse were less than 8 degrees. When we didn't get any signal back from the lander, we took the new data that we collected in the previous week, okay, and plotted it up and found a hole with a 16-degree slope on it. And that is precisely where the lander landed, okay? So in addition to the engineering challenges associated with landing on Mars, there are also technical challenges. It is difficult to find a lander on the surface of Mars. This is the polar lander, and what we're doing here is degrading it. And the best resolution images that we can take from orbit is 1.5 meters per picture element, and this is what that lander would look like, okay, if you looked at for it. So it has, you can't find the lander, and we won't find Beagle either, okay. This is Beagle. Okay, that is the last picture taken of Beagle as it separated from Mars Express a little more than a week ago, and this is where Beagle landed. It did land. Okay, in the Isidis Basin. It was on target to land. There was nothing there to stop it. Okay, so it went in, and we. This is the landing area. These streaks here are dunes. Okay. And there will be a search for it, but the size of the lander on the surface is smaller than one picture element. It's only about 2 feet across, and 1.5 meter resolution. So it's smaller than a picture element, so we won't be able to see it. Okay, the two Mars Exploration Rovers The one that will be landing later this month on January 25th will be landing in an area called Sinus Meridiani. And this is an area that has a chemical signature that is suggestive of hematite, which is an iron oxide that precipitates out in warm water. Okay, so it's thought that this was an ancient hot spring, and you can see why we would want to go there. And then tomorrow night the landing is in a crater called Gusev, and this crater here has a channel flowing into it, and this is thought to be an ancient lake bed. So these are two absolutely fascinating places to land, and this one it gets pretty windy in the afternoon. Okay, so the probability of success that we calculate for both of these landers is greater than 90%, but those only take into account the errors that we know about. They don't take into account holes that we haven't mapped yet, okay, or windy afternoons, okay. Okay, this is, the next thing I'm going to show you is just a quick movie, but this is just a comparison of the Pathfinder rover, which many of you are familiar with, which is a nice little thing, which was about this big, and that's the Sojourner on the surface. And these two landers, instead of 11 kilograms, they're 185 kilograms. Pathfinder went maybe 10 meters from its mothership. These have the ability to go hundreds of meters. Okay, so here what NASA is doing is striving towards mobility on the surface, the ability to go out and look more broadly. And so now what I'm going to show you is just a simulation of, I think I better save that because I don't know what I did to the file. Just going to show you a simulation here of what the launch and landing of the Mars Exploration Rover spacecraft. These are two identical spacecraft. MER-A, or Spirit, is landing tomorrow. MER-B, or Opportunity, is landing on the 25th. Okay? And before I show you this movie's about 6 minutes and some seconds, and then we'll be done. And what you should realize is that everything up until the spacecraft goes into the atmosphere in this movie has already happened. Okay? This is a simulation. It's a computer generation of what we hope is going to happen. But up until the spacecraft gets into the atmosphere, everything has happened precisely as you see in the movie. Okay, so everything has worked perfectly, and there's every hope that everything is going to work perfectly towards the end too. So let's go full screen now. Okay. Okay, so this is going to start with the launch. These rovers were launched on a spacecraft called a Delta down at the Cape Canaveral Naval Air Station. They're actually not launched at Kennedy Space Center. They're in an Air Force station across the Banana River. And we like to launch things in Deltas because Deltas are very dependable launch vehicles. They have greater than a 95% success rate, which is very, very good for expendable launch vehicles. And the thing about this launch vehicle is that it spins up to target accurately, just like throwing a spiral in a football. Okay, but because of the fact that it can't be reconfigured as it's flying, there's a 2-second launch window. So if it's too windy or if a fishing boat gets in the way, you have to wait 12 hours because you can only program it twice a day. So there's the Delta taking off. It has 9 small solid rocket motors here that are going to come off in groups of 3 for stability. So there's 3 of them, and there's another 3, and then you'll get as it comes out of the atmosphere, there go the last 3. Okay, so most of the energy is to get out of the Earth's atmosphere. Okay, and then a kick motor starts up here and sends it in the approximate direction of Mars. Then we're not in the atmosphere anymore, so we don't need a nose cone, and that's the heat shield that's going to come off. And then it's going to spin up. You're going to see it here spin. It goes up to about 80 RPM. And so, again, it's like a spiral football. You can now target it very accurately towards Mars. And this is it's a very touchy maneuver. And then we don't need to be spinning that fast anymore, so we use yo-yos just like an ice skater slowing down and putting her arms out take the momentum away. And then then you just go to Mars. Okay. Okay. So and that all happened in June and July. Okay. And so then we get to Mars, and now this is where the excitement comes. And then tomorrow night, this is what's going to happen. Okay. So the spacecraft is going to come in. It's going to jettison that, which it doesn't need anymore. It's going to hit the atmosphere going about 20,000 kilometers an hour. For about a minute, it's going to see temperatures about the temperature of the surface of the sun, or 5,000 degrees. Okay, the atmosphere, even though it's thin, slows it down a lot, and it actually gets down when it gets to Mach 2. It brings a parachute off. And then it quickly decelerates, because 15 seconds later you're subsonic, okay? And when it becomes subsonic, then it's going to lose the heat shield. It doesn't need that anymore. And then 20 seconds after the heat shield goes away, it deploys a bridle here that has the lander down at the bottom. And this bridle is about as wide as a bootlace, okay? Then about 20 seconds before landing, the airbags will deploy. And when we get about 40 meters above the surface, retro rockets fire and bring it down, and it hits the ground at 40 Gs. Okay, and this movie doesn't at all do justice to what's really going on, because this thing bounces for 10 minutes. Okay, because G is only 3.7 meters, so you get a lot more bouncing, and it's going to take it 10 minutes for it to come to a complete halt, and that may be all we find out tomorrow. Okay, there's some chance, depending on the configuration of the thing coming in and the way the parachute is angled, that we won't get the semaphore tones right away that we're using to track this. It could be as much of a day till we get signals back, but we hope it won't be that long, and it could take as much of a week for the rover to come off its stand right here. So this is camera. These are stereo cameras here, so you get a depth perception like your eye has. It has navigational cameras. It has spectral cameras, and the thing about this is it's going to have people driving it out at the Jet Propulsion Laboratory. So you can actually make decisions about what you'd like to explore next. And it'll be like I said, it'll be about a week until you start to see panorama images like this. So this, as I said, this has mobility. This can go tens of meters a day. This is the high gain antenna right here. This spacecraft can go direct to Earth, or it can go to the Mars Odyssey and Mars Global Surveyor spacecraft at a higher data rate. Mars Odyssey is the provider of choice for a data link, because it gets the highest data link. So this it can go over the horizon. Now, what these rovers have the ability to look at, they'll be able to take images to get geologic context. There are a number of spectrometers on there to measure chemical composition. And one of the things about Mars that we talked about is that it's very dusty, and everything's covered with a cover of dust. And so we want to be able to see inside rocks to see what the pristine rocks are like. And so this rover actually has a drill on it that's called a rock abrasion tool, where it can come out and it can actually drill away the outer rinds of rocks. So you can go inside of a rock and measure its pristine chemical composition, and also look for evidence. So in this, there's a camera in here too, where they're going to get millimeter resolution images of what the rocks look like. Okay, and there are also spectrometers that are very well tuned for iron-bearing minerals, because the second site will have a high concentration of iron-bearing minerals. And the nominal length of this mission is 3 months. It's late summer now. These things are battery-powered and solar cell-powered. And Mars is dusty, so when the sun starts getting low and when you get dust on the solar panels, you lose enough energy to keep this thing communicating and also to keep it warm. Okay, this thing doesn't want to be above room temperature, and it doesn't want to be too much below room temperature either. And so if everything goes well tomorrow, that's what you're going to see. And what I can tell you is there was a maneuver done the day after Christmas to hone the targeting of the spacecraft. The burn lasted 3.4 seconds, and it changed the velocity of the spacecraft all of 2.5 millimeters per second. Okay, it shifted the landing site on the surface about 50 kilometers to put it right in the middle of the landing ellipse. And all indications as of this afternoon is that everything is nominal, that another adjusting maneuver won't be needed. The sequence to execute the entry, descent, and landing is on the spacecraft, and it will execute tomorrow unless we do something, which there's nothing to do because everything looks like it's nominal. So we hope that nature will be on our side tomorrow, and we hope that we've been smart about what we've done. But it's a thrilling time for Mars, and hopefully tomorrow will be a good day. And I'll stop right there.
Take a few questions. I'm sure there's plenty of them.
I heard there was a communication problem. Just reading the paper recently. Is it possible now?
Not with the MERS.
No.
No.
So everything's
Beagle, there's a communication problem with the Beagle, the European.
Oh,
yeah.
Okay.
Anybody over here? I'll try to go back and forth.
I wondered about if it's so dusty there, what kind of protection you have for the mechanics of the machine. The dust doesn't affect the.
Oh, you know what? When you go in and you design these things, you don't want mechanisms, you don't want pyros, you don't want anything that moves, arms, but they have all this. Okay, and it's basically the way that you get around that is to engineer things to extremely fine tolerances so dust can't get in. Okay, and that's you've got to do the best you can do. So.
I just had a quick question. When you were talking about the north and south poles of Mars, you said you were going down to the North Pole. Don't you usually go up to the North Pole?
Well, not if it's lower on the planet than everywhere else.
Yeah, but how? Usually, the north part of anything is usually the highest.
But it's not on Mars. It's a different planet.
On that regard, the slope from south to north, is it, I saw us to say, is it continental formation forming that slope, or is it an open?
Yeah, that's kind of a technical question, but it is isostatic.
There, okay,
So,
okay.
yeah. So,
are you at all concerned about taking microbes over there and then, on the rover, and then when you're looking for microbes in the future, finding Earth microbes?
There are strict criteria for levels of sterilization for anything that's landed on Mars. But the truth of the matter is that we have contaminated Mars already and for a long time. And because orbiters don't have to go through the same contamination procedures, but orbiters have crashed on Mars. Okay, but we have rocks on Earth that came from Mars, so Mars may have contaminated us too. So.
Well, that was part of my question, was the fact that earlier on the contamination procedures were based on our understanding of the survivability of microbes and things, and since the Vikings and things like that, we found these black smokers at the bottom of the ocean with microbes surviving at 400 degrees C and things like that, water. So how do we really know that we're not just, if we have a pristine environment for microbes potentially in Mars, we aren't going to just come there one day and find, this vast proliferation of forms which may have some link to the Earth forms, but they've mutated dramatically in all the radiation environment and everything like that.
Yeah, it's a hard question to answer, and the National Academy is looking at that right now. The criterion for sterilization have changed since Viking, and they've gotten more strict, and there's another panel convening to relook at them again. But you can't be 100% sure.
Thank you. Two hopefully very simple questions. One, is there a very powerful wind on Mars? And the second question I'd like to ask is the water on Mars similar to the water on Earth?
Let's see, wind on Mars. If you were on Mars and you could stand there without a spacesuit, it would feel as windy as Earth feels on a windy day, even though the atmosphere is much thinner because of the intensity of the wind. Okay, and the water on Mars is H2O. Okay. And there could, in the North Polar Cap, be some amount of carbon dioxide mixed with that. It's something called a clathrate. But you would have to go there and sample it. The spectrum looks like H2O.
Thank you.
Yeah.
Just really simple. How long does it take you to send and receive a signal from the lander? Like, if it was in danger, how would you get it out of the way fast enough?
Oh, you wouldn't. No. No, it's the signals that it sends back are information only because the sequence is preloaded. Okay, the one-way light time to Mars is about 4 minutes, and the two-way light time, so it's going to be 10 minutes. But then, if you saw that there was a problem, you'd have to think about what to do about it, and then anything. I mean, the reason that I'm going to say nothing's going to happen before tomorrow is that at this point now, anything that you do, you don't know you don't have time to think out how it's going to affect everything else in the system, and you really run the risk of making things worse. What they've done up until now, everybody has thought about and everyone understands. Okay, and what you want to execute is what you've thought about, not what something. So the signals that you get back are really just for information to say it got this far, it got this far, it got this far, and it's going to send back a series of tones, and these tones are going to say that critical sequences were executed, and there will also be tones sent back if some important reading is out of a nominal range. Okay, so that at least you can go back and we got a second one getting there January 25th, so a week from Monday, I'll be back at the Jet Propulsion Laboratory trying to figure out what do we want to change about the second one based on what happened with the first one. So.
Yes, I wondered, could you just go briefly into the kind of spectrometers you have there? Are they emission spectrometers? Are they absorption or something of that sort? And what sort of wavelength range do you cover?
It's actually panchromatic thermal emission, and it's 0.2 to about 40 microns, so it gets into the thermal. Okay.
You talked about an 8 minute. Was it an 8 minute delay in the light turnaround time?
But it's more than that because there's delays in the deep space network. You never get the signal precisely when you want to. There's just delays in the system once it gets to Earth.
No, I was wondering what the experience must be like trying to drive that rover under those kinds of circumstances. Is there any autonomy?
You don't. It's not like a dune buggy or something. This thing is, you're going millimeters an hour. Centimeters an hour on a good day. Yeah. So.
What are the minimum requirements for a Spirit or Opportunity to be able to send a signal? In the video, we saw panels unfolding and antennas being raised. What would be the minimum requirements to just be able to get a signal from one of those two landers?
Let's see. Well, there will be signals sent back from the spacecraft as it's coming into the atmosphere. Okay, and then once the spacecraft gets on the planet and sort of deploys the pedals there, the first thing that comes up is that round-looking thing, which is the high-gain antenna. So there's a high-gain antenna and there's a medium-gain antenna. The high-gain antenna can go direct to Earth, but it's directed. So I'm not sure what you mean by minimum requirement. I mean, the batteries are powered, okay, so it has to have enough power to send a signal. And if the first thing it's programmed to do is to send a signal and say, I'm here, Okay, so, and then if it doesn't do, and it goes through this sequence where it keeps sending it, and then if it doesn't hear something back, then there's a whole bunch of other sequences that it goes through. It assumes it's in the wrong orientation, so it starts to rotate it around and look for a signal. So.
Could the patterns that you saw of the meandering streams be formed by either wind or lava flows? Are there other explanations for, other than water, that could have formed some of those features? For what looks like a meandering river or a cut-off lake.
Yeah, those patterns that you saw are indicative of a fluid with a lower viscosity than a lava. Okay, and a flowing lava is about 1,000 poise, and water's like 1 poise. So
could other fluids flow on Mars?
Some people have proposed liquid CO2. Okay, but for liquid CO2 to be stable on Mars, it requires a 6-bar atmosphere. So it requires an atmosphere that's 6 times as dense as the Earth's atmosphere, and it's hard to envision where a 1-bar atmosphere went on Mars, let alone a 6-bar atmosphere.
How are decisions made to decide where the rover goes each day?
There is a principal investigator for the landers, and there are meetings held with the scientists, and it's a meeting that includes scientists and engineers, because it's a question of not only where is scientifically interesting to go, but where is technically feasible to go within the engineering constraints of the rover. So basically, meetings. Yeah. It's like everything else gets done. Yeah. So.
Question?
How long will the rover last before it doesn't work anymore?
It's programmed to last 3 months, but if we get a signal back tomorrow, it's going to last longer. So because they've been over-designed as they need to be.